Yeah, we'll be talking through time complexity and space complexity. So it's a carry on. It's what we've talked about from the previous section, but now we're going to go into more detail. Um, Before we do that, real quick, let's go ahead and talk about Piazza. Essentially, I want you all to know that we've had a week and a half of class, and 100 people have posted on Piazza. There's 100 posts already, which is great. I love it. More than 100 posts have been posted, but we do realize that given how many posts there are, there needs to be some ground rules to make sure that we're posting effectively. Essentially, when you are posting, I want to make sure you're descriptive with post titles. What that means is, like, for example, instead of saying homework 1.1 in the title, make it more descriptive. Talk to me about what you're stuck on, what you want, what your question is, and how you want it to be answered. So maybe you're stuck on validating distinct elements, question mark, and that might be your question, right? This is really helpful because, for example, you can search on Piazza. You can search for a problem that other people might have already asked about. And in order to make search useful, you have to make sure you're adding enough description into your title as well as the body of your post in order for the search to pick up. So for example, if you're stuck on Replit, you can type in Replit and you can see some folks had some issues on Replit, and we were able to answer them. But just make sure that your post title and everything is descriptive enough so that we can very easily figure out what you're asking about. This really helps the TAs and the other students who might be looking through posts and want to make sure that we're answering new posts. If you see homework 1.1 like 18 times, it's harder to keep track of which ones you've answered and which ones you've not, right? Consider whether or not your posts can be public or private. So if you're working on specific code and you're trying to debug something specific, making a private post is the right play. But if you think your question can help other people and it's not debugging specific code, making it private is actually a disservice because other people might ask the same question. So in that case, please make it public. Sometimes you'll be asking a private question, making a private post, and I'll actually ask you, hey, can you please make this public? And I will expect you to do so because typically it's a question that I think would really help everyone else, right? You can make yourself anonymous when you post publicly. There's an option for that, but it's always important to just consider from the get-go whether or not you should make your post public or private. And you can always make yourself anonymous if you go public. Private posts on homework should always go to all instructors. What I mean by that is if you have a Piazza post about some personal thing that you want to talk about, whether it's like logistical or something that goes straight to me, then you can always do that. But if you're stuck on homework, please make it so that it goes to all the TAs and me. If you just send it to a single TA, maybe that TA isn't answering Piazza that day, so you might get a really late answer. So if you just send it to a certain instructor, you might not get an answer on time. But if you send it to all instructors, then whichever TA is on shift that day will be able to answer your question or point it to the instructor who needs to take a look, right? There are sometimes people make a post and instructors or the TAs know that it should go to me and they let me know. If you are editing code and posting code on Piazza, for example, like this is nice and beautiful. It's nice and beautiful because there's an option to set the code block which formats the code so that it looks like an editor, which is super important when you're reading. It's really hard to read a code when it's typed in like normal text. So use the code block in order to make sure your code looks beautiful and it's easy for the TAs to help you. All right, moving on. So today we're actually going to talk about function runtime. We're going to go into more about function runtime, ask some more specific and detailed questions, do a little bit more specific analysis, especially around best case, average case, and worst case. With the time we have afterwards, we're going to talk about time and space trade-offs. So we're going to look at two sum. And we haven't had time to do this for any of the other sections. So we'll probably skip big O, big theta, and big omega and cover that next lecture instead. And then we'll end with takeaways. So if you remember from last lecture, the most important thing to remember is that when you're trying to find the runtime of a function, for example, when we did it up here, when we tried to find the runtime for functions like countdown, the first thing we needed to do is to define what in means, right? Which is going to be defined as the size of your input, but you need to figure out exactly what that means for a specific problem. Then you have to understand and analyze what the function is doing, count the number of steps needed for each part of the code, and then use big O notation to find the overall runtime of the algorithm. If you're not sure what I'm talking about, watch lecture 3 again, go over the slides. It's really helpful. In fact, I would encourage you all to be really, really diligent about studying the first 2 weeks of class. This stuff will be coming back over and over and over again. We're going to talk about recursion throughout the class. We're going to talk about runtime throughout the class. We're going to use pseudocode throughout the class. So if there was any class lectures to really take good notes on and make sure you understand and work through the exercises, it's these 2 weeks, right? These 2 weeks are foundational. Don't treat them just like review. We will be using the information in these 2 weeks basically for the rest of the semester. So this was from last lecture. Hopefully it's familiar to you. But today we're going to go into properties of algorithms. So what that means is that beyond just asking how fast does a specific algorithm run, we have more specific questions to ask when analyzing an algorithm, right? If you remember from Bloom's taxonomy, analyze means you take an algorithm and you break it down into its constituent parts. And in this case, there's more questions in greater detail that we can ask. For example, what is the best case runtime? What is the worst case runtime? What is the average case runtime? And how much space is used? These 4 questions we're going to spend a lot of time on this lecture. And the idea behind them is that we still care about the behavior of an algorithm as we increase the size of the input. So when we're asking about the best case runtime, for example, we're not just saying, oh, if you're sorting a list and I give you an empty list, that's the best case, right? That doesn't give us any useful information. We instead need to talk about when a input increases in size, is there some characteristic of that input still, regardless of the size of the input, that would allow us to figure out the best case? So I haven't defined exactly what a best case, worst case, and average case, like what that even means or like how to find it. We'll talk about that very, very shortly. But one thing you should know right now that I'm going to be repeating over and over again that you should like write down and memorize is that when we ask about these questions, we're not talking about specific inputs. We're not talking about specific sizes. So go ahead, everyone in chat, type in to chat. The size of the input is not relevant when answering these questions. I must not fix the size of the input. The size of the input does not come into play when answering these questions. Type that in chat. Because I promise you, even if you type this in chat and I'm making a big deal out of it and everyone feels silly typing this in chat, that some of you will still miss this on the next quiz. Some of you will still miss this on the exam, right? Because that's what happened exactly last semester, right? Even though I'm making a big deal about this, even though I'm metagaming and talking about how typing this in will still make you miss this, some of you at least, it's still going to happen, right? The size of the input, we should never say, okay, the size of the array like matters when we're talking about best case. We can't say, oh, if we have an array that's empty, that's never going to be how we describe the best case or the worst case or the average case. Okay, moving on. So why do we even bother with these questions? These 4 questions from before, the best case, the worst case, the average case, and the space. Well, if we think about these properties, they actually allow us to decide when there's 2 different algorithms that solve the same problem, which algorithm to use, right? So it effectively gives us a way to think about a problem and evaluate 2 different algorithms such that we understand them deep enough to decide when we use which algorithm. They also are useful when we are trying to make a slower algorithm fast. So if we know exactly what the worst case is, we know exactly where the worst case is in the code and what inputs cause that worst case, we might be able to take that and make it faster. If someone's asking, whether or not we're going to use big O notation for the best case. Yes, we will. And we're going to talk about that very soon. So don't worry, you're going in exactly the right direction, but we'll look at an example after this. So if we're looking at this situation, we asked about these questions basically because if we can identify which cases are slow, we can maybe speed them up, right? Oftentimes you'll have to make explicit trade-offs. So if you're working on a computer with very limited space, right? Like imagine you're working on a smart speaker or something like that. Something that is fundamentally not very good hardware. It doesn't have that much memory. It doesn't have that much CPU. You might be okay using a little bit more time to compute your algorithms to carry them out rather than using space, since this piece of hardware is kind of low level or not very good. But if you're on a fast computer with lots of memory, then maybe you want to instead use of use more space, right? Sacrifice space so that your algorithm or your program, whatever it is, runs really, really quickly. And being able to answer these questions allows us to actually think about those space-time trade-offs. And we're going to talk a little bit about that at the end of the lecture here. All right. So how do we actually answer these questions? All I've done is kind of given some brief, maybe unhelpful definitions. So let's go and talk about this in more detail. When we're talking about best case, what we're really asking is what type of input. Let me go and annotate this correctly. Instead of what's the input, what's the type of the input that would cause the algorithm to finish quickly, in other words, take the least number of steps, right? So if you remember for lecture 3, we looked at an algorithm called mostly harmless. And mostly harmless exited right away because it had a integer as input, some z that gets passed in, and we check to see, we set I to z real quick, and then we check to see if I is either even or odd. In either case, we returned right away. Well, if we do that, that means that z will always return out of the for loop after the first iteration. Before the first iteration even finishes, we're going to know that I, which is z, is either even or odd, and then we'll return, which will take us out of the for loop as well as the method itself. Well, that is kind of what we're trying to think about here. What cases in the code, whatever algorithm we're looking at, what cases in the body of the function cause us to take the least number of steps, right? How can we exit right away? A worst case, right? The opposite of this is where the input will cause the algorithm to take the most number of steps, right? We call this the adversarial case, or my enemy has my code case, right? Imagine your worst enemy, and they have your code and they want to make you look bad. They're going to pass inputs into your code that will take your code the longest to run, and that's kind of what the worst case means. Again, the size of the input doesn't ever matter. So it could be something of size 10, it could be something of size 1,000, but what matters is the properties of that input that's irregardless of size will help dictate what behavior your algorithm will take. Um, and we'll see that very soon now. So if you're still a little bit unsure what this means, don't worry, we'll look at it in a second. Average case is just what typically is the type of input that the algorithm will see. So that's something we'll look at as well. But in this case, for example, if we're sorting a list, it's probably like I pass in a randomly ordered list, right? A list with no particular order. That's typically what's going to happen when we are sorting. And in each of these cases, make sure that your inputs, right? We're talking about the type of the inputs. The inputs are not specific inputs. They're not specifically sized, but you instead can describe the inputs such that the properties that you're talking about apply to increasingly larger inputs that would still have the characteristics you identified. Okay, so let's look at a specific example now. Let's actually look at a problem and the algorithms around it. So we're going to look at the best case to worst case and the average case runtime for two algorithms that solve this problem. Given an input of numbers, right, an array of numbers, and some target x, we're going to return the index of x within ARR if it is in ARR, otherwise return -1. What does that mean? Well, here's some examples. We have an array and a number that gets passed into find index. Find index is going to take these and return the index of where, in this case, 4 is, right? So 0, 1, 2, 3. Index 3 houses number 4. 4 is the number we're looking for, which is why 3 comes out. When we're looking for 70, well, that's index 0, 1, right? So at index 1, we can see the 70 and we'll return 1. And then if we're looking for 10, well, there's no 10 in this array, which is why we return -1 here. Let us see if we have another example. If we say, for example, find index, and we pass in the same arguments as before, but we're looking for -2 this time, I'll give you 10 seconds to type it in chat. Don't hit enter. What should the output be to make sure that everyone understands this algorithm, right? Everyone understands this problem, what this algorithm is supposed to do. What should be the output? Go ahead and type it into chat now. What should be the answer? Okay, we're getting a bunch of 2s in chat, right? Because index is 2 gives us this -2. And since this is what we're looking for, we should output 2, right? So this isn't hopefully anything too scary. But let's go ahead and look at our first algorithm in this case. We have an algorithm called find index. It has the input and the output as defined here. We're going to look at the pseudocode version of this. And for each index I and corresponding element E in the array, we're going to check to see if E is equal to our target, return the index. Otherwise, just return -1 at the end if we've gone through the entire array and we couldn't find it. Right? So if we have this example from before, what we'll do at first is we're going to start saying that I is equal to 0, which means E is equal to 9. And we're going to check to see, is X equal to 9? Well, it's not, because X right now is -2. So we keep going. I is equal to 1, and then E is equal to 70. Typing is hard. There we go. 70 is still not -2, right? So this if statement here is not true. So we skip it and we go to the next one. What should be the new I and the new E? Type it in chat if you know. The new I in this case should be 2, and the new E should be what? -2. That's right. Right, so I in this case, if we already saw index 0 and index 1, that means the next index is 2. E is going to be -2. We know that that E matches the X we care about, which is -2, which is why we would return the I, which is, getting 2 out. All right. So now that you've seen how this code works, hopefully it's not too scary. We're going to go ahead and try to answer the following questions, right? The best case, the worst case, and the average case. That's the 3 questions we're going to ask. We're going to worry about space in a little bit after the break. But I'm going to give you all 20 seconds to answer the following question that I'm going to put in yellow here. What is, that's not yellow, that's red. What is the type of input that would cause find index to return right away? Don't type it in, type it in chat, but don't hit enter. All right, I'll give you another 15 seconds, and then we'll all answer all at once. Okay, go ahead. What do we have? Okay, some of you failed. Some of you failed the test. All right, some of you said the empty array. Thank you all for failing this test, because what did we just say like 10 minutes ago? The size of the input should not be a factor when we're trying to figure out the best case. So some of you said the empty array, and that is incorrect, right? So the empty array cannot work here. This is wrong. I'll even put it in red, right? And you all fell for it, which is great, right? It's better to make this mistake right now. Mistakes are totally normal. And you learned something, hopefully. You'll remember it more thoroughly for next time, because I poked fun a little bit, tiny bit at you right now. Right. So the empty array is incorrect because that's only one specific input. It does not generalize, and therefore we can't use it. Right. So that's a big fat X. But if we can say, why is this? Okay. If we can say that the array, the best case, we'll do it in green. The best case is when target X is equal to array of 0. The first element in the array is the target we're looking at. Then that's good, because for example, we can do find index of 1, 0, 0, 0. Like, just imagine having a million zeros in here. And then we're looking for 1, right? So we'll get an answer right away, because in this case, as soon as we find the 1, we're going to return it, right? We return the corresponding index. In this case, we'll return 0, right? So when the target X is equal to array of 0, then we're good. And the best case here, we just need to count how many steps that it took. We know that we go through one iteration of the for loop. Let's imagine that this for loop, the first iteration, we take like 2 steps. This if check is 1 step, this return is 1 step, so 4 steps total. If it's 4 steps total, then the best case is going to be O of 1, right? Because no matter how big our array gets, whether it's 100 elements or 1 million elements or 1 billion elements, it's always going to take those 4 steps, right? So our best case is O of 1, because we can come up with the best case where the target is the very first element in the array. right? So the empty array does not work here. Try not to fall for that trap in the future. I will definitely put it somewhere in a quiz later on, and it just straight up ask you like what you're not supposed to do when you're trying to figure this out. Now, on the other hand, what is the worst case? I'll give you 10 seconds, type it into chat, but don't hit enter. What is the worst case in this scenario? If you know that the best case is where you find it right away, it's the very first element, then what would be the worst case? All right, type it in chat if you know. Okay, so people are typing in last element. If we wanted to add more information to that, we would say that the worst case is when we either cannot find the element in the array or the last element is the target. All right, so if you can't find the target at all, we're still going to go through the entire for loop, iterate through all in elements. Ooh, I made a mistake here. We should have said that n is equal to the array length, right? You should always define what n is in this case, and I failed to do that. But you should always take the step one and define what n is. In this case, n is the array length. And the worst case is if we have to go through all n elements and we still can't find it, we'll return -1, right? So the worst case here would be O of n, because as the size of the input increases, like if I give you 1,000,000 elements, it's going to take 1,000,000 steps. If I give you 2,000,000 elements, it's going to take 2,000,000 steps. If I give you 4,000,000 elements, it's going to take 4,000,000 steps, roughly speaking, right? This big O here helps a lot. Now we take the last question. What is the average case? What do you think should be the average case in this case? What do you think should be uh, the case that describes the average? So the element we care about is somewhere in the middle of the array, right? And this is something that totally makes sense. Just like, on average, we're going to find the element somewhere in the middle. It's not going to be at the very beginning. It's not going to be at the very end. It's probably somewhere like halfway through on average, assuming we have some random array. And if that's the case, that means that we are going to look and iterate through n over 2 iterations. But n over 2 is n O of n, right? There's no such thing as O of n over 2. I mean, there is, but O of n is kind of the same thing, right? So in other words, O of n is the set of all functions, right? The bag of all functions such that they work or behave very similarly to a linear function, right? So we don't care about this over 2 section, if you remember from lecture 3. Lecture 3 had us talk about how we use big O for algorithms. And it just means that we can ignore any leading terms, any multiplicative factors. So this 4 here, for example, when we're saying 4n cubed. So we can drop the 4 in this example, which means in the example that we have here, we can drop the over 2. All right, and which means that the average case in here will be O of n, where n is the size of the array. Someone's asking, how did I get O of 1 here? Well, O of 1 is where we have an array of arbitrary size, and the first element in the array is equal to the target that we care about. So no matter how big an array you put in, you can always design an array that looks like that. So that's the best case we're looking for. And if that's the case, that means no matter how big the array gets, it'll take a constant number of steps because we just go through the for loop, and then it goes through the if, and then we return at the end. Since we don't consider the empty array for the best case runtime, should we consider the situation where the target index is not in the array for the worst case? Yes, because the target index not in the array does not depend on the size. An empty array has a fixed size. An empty array is size 0. An array that doesn't have the target, it can be like 10 big, it could be 20 big, it could be 1,000,000 big, it doesn't matter, right? So that's kind of the most important thing here. All right, moving on. Someone's using big theta already. We're probably going to talk about that next lecture. But big theta is not how I would not use big theta in this case. I would just use big O. Big theta is here for providing a lower bound, and we want the upper bound on how the best case is described. In fact, theta sorry, not big theta, big omega. That's what someone in chat is typing. But in either way, I think big O is appropriate. Big theta could be appropriate, and big omega would be incorrect to accurately describe the best case runtime. All right, so we're looking at another example here. Just to be absolutely clear, this is a second function, right? It's literally called another find index. This is the original one. This is the new one. They're different. I'm going to give you all about 2 minutes to try to understand this function and try to find the best case, the worst case, and the average case accordingly. Right, so I'm actually launching a poll now. Everyone has a chance to answer. We'll give 2 minutes to try to understand this function and to try to figure out what the best case, the worst case, and the average case runtime should be. In this case, n will be the size of the array, so hopefully that's obvious. But from there, you're going to have to figure out what we do next. So again, the goal here is to understand what the function is doing, try to figure out the number of steps it'll take, and then come up with examples of what types of input will cause the best case to happen, what types of inputs will cause the worst case to happen, and what types of inputs will cause the average case to happen. It's been about a minute, and about a fourth of you have answered, which is great. But start making sure you are heading toward an answer, even if you're not 100% sure you're right. Remember, I never grade these answers. I never give you a grade on whether or not you're correct. I just want you to think about how you would solve this problem on your own and practice that right now so that when we go over it, you have something to think about. Don't just think that lecture is a, inactive, boring, like not really participating type situation, because you're not going to learn as much. You're not going to remember as much, right? The reason why I ask you these questions and the reason why I always harp on this is because I think it's important. Someone's saying that the poll is disabled. Well, 50 people have answered it so far, so maybe it's something on your end. I'm not 100% sure. Okay, it's okay now. Great. All right, so participation is for grade, as I said on the syllabus in day one, but it's also here just to help you learn. Right? So if we look at the results here, according to the results, a lot of you thought that the best case scenario is going to be O of 1. And a lot of you thought that the worst case scenario was O of n, the average case is O of n. Now, I'm curious, can anyone who picked O of 1 for the best case, does anyone want to share what their justification is? Go ahead and type in chat if you know. I'm just curious what you were thinking when you were coming up with O of 1 and what sort of examples you were thinking in your head that would cause us to run in O of 1 in this case. Over half of you thought that it was O of 1 for the best case. So hopefully some of you are brave enough to proffer an answer. Okay, so people are saying first element. The best case scenario is when the desired element is in the first. Yeah. Okay, so a lot of you are thinking the same runtime here. Someone's asking equals instead of double equals. In this case, equals is like fine in pseudocode. You can write double equals, it'll mean exactly the same thing, but I treat the equals in this context as checking for equality. But in this case, the correct answer for best case is O of n. In fact, all of them are O of n. Someone in chat already gave it away. And I'm doing this not to like make fun of anyone, but you all like nearly more than half of you got the first answer wrong, right? And that's on purpose. I put this question here to trick you, like deliberately. So thank you for falling into my trap. You all got baited. And the important thing to remember, like why is this O of n, is this part here. In the previous function, we returned right away. We returned I as soon as we found it. We found an E that's equal to X, right? But here we don't do that, right? Instead, we set results equal to -1. And then when we find an element, we're going to go ahead and just keep looking afterwards, right? We keep going. There's no return here. So the kind of key here is that when you're iterating through, the difference between this function and the previous function is the lack of return in the middle of the function, right? Since you're not returning early, there's no way you could pause. This is the previous function where we return I, and the new function, we're just setting result equal to I, right? It's a subtle change, and a lot of you missed it, which is why I'm bringing it up right now, right? We only return result after we've looked through every single element, which means that in the best case, the worst case, and the average case, they're all going to go and take in iterations no matter what, right? So don't feel bad if you got it wrong. As you can see in the poll results, more than half of you got it wrong, and that's fine. But the key here is that you have to really understand what the function is doing before you give an answer. And you have to think about whether or not the input that you're imagining behaves on the code the way you think it is. All right. So the average case and the worst case, I'm not going to explain it in detail because we already know in this case, it's because we're iterating through every single element. Moving on. Let's go ahead and take a break. We're going to take a 5-minute break. We'll come back at 6:35. And if you have any questions or concerns about what we've just talked about, feel free to ask now. Things you should know. We're on break, so you can, this is the normal part of the time where you can go to the bathroom, get a drink of water, check your phone. We'll come back at 6:35. But things you should know while we're here is that homework has been released. It's on the course website. And it's due on Thursday because someone said, hey, it'd be nice if we could do a homework party and then actually have a few days to think about the information from the homework party and work on the homework, as opposed to having it due on Tuesday, which means you only really have like 2 days, right? Watch the video or attend homework party, and then you have 2 days to finish it. That means homework 1 and all homeworks going forward will be due on Thursdays. Homework 1, if you click through, you can create an assignment for you, a repo, and start working on it whenever you can. And if you're stuck on like how you're supposed to work on it, just click on the homework 0 intro video, which should help and give you advice on how to do that. So make sure you check out this video. It's super important. And if you're new to the course, this is something I expect you to watch and do for both homework 0 and everything going forward. Anyone have any questions about the code? Other things you should know, we have a programming club events happening tomorrow, Saturday, and Sunday. If you're interested in learning more about Java, for example, you could try to build tic-tac-toe on Friday. If you're more interested in learning about strings and arrays, that is something that we're covering on Saturday at 2 to 4 Eastern time. And then we have some mock interviews from 2 to 4 on Sunday. So Programming Club is a club, if you haven't heard about it, here to just help you get better at programming, no matter where you are. If you're a beginner, if you think you're maybe not super good at programming, or if you feel like you're really advanced, there's something for everyone in the club. Is today Thursday? Yes, today is Thursday. In the homework, are we allowed to import data structures if we need them for our solutions? Yes. You can use anything in Java that utils. But if you use something more exotic or I guess not commonly used, make sure to ask on Piazza. But if you're just using like an array or a hash table or a hash set, that's totally fine. If you want to use lambdas, sure, go for it. If you want to use Java 8 stuff, yeah. I think it compiles in Java 10 right now on Replit, and our auto graders will probably know about lambdas too. All right, again, we're on break, so feel free to chill. If you have any questions about find index or anything else, now's the time to ask. How's your week been, by the way? We got 2 minutes. Everyone have a good week so far? It's week 2. Very tiring, but fine. Been doing good, can't complain. Super busy, tired. Scored more PS5s. Are you just buying a bunch of PS5s to flip? I'm not sure if I like that. I mean, I'm not the boss of you, but at the same time, all those poor people. Fighting the urge to dust off Animal Crossing and pretend real life doesn't exist for a while. I feel you. I've been playing a lot of Mario Kart outside of class. The last couple of days I've been working from like when I wake up all the way to when I go to sleep. Like you'll see me answer emails at like 3 a.m. your time, which is like 12 a.m. my time, which is still pretty late. Um, what character do I use the most? I like Luigi a lot, but I don't have like a strong preference for Mario Kart. I'm like a pretty casual player. I don't play online. Right now, I'm just trying to clear and get 3 stars on 200cc for Mario Kart Deluxe. Hopefully, you all have a chance to relax and rest up over the weekend. Maybe Friday you'll get some time to hang out with people or spend some time recharging. Whatever you do to recharge, I hope that you are able to do that. You got to get Mario Kart. Just don't get Mario Kart the same way you're getting PS5s. Don't try to buy up all the copies and resell them. You can't even do that anyway since they have digital copies. Digital Animal Crossing was so hype. It's very zen. Uh, I played it a while last year, and the music's really nice, especially if you go on Spotify. There are remixes. All right, so we're going forward now. Um, let's go ahead and take a deep breath and type space in chat if you're ready to learn again. Right, we're coming back from the break. Space, the final frontier. At least the final thing we're going to cover during lecture today. So similar to time complexity, space complexity requires you to understand what the function is doing step by step, right? So every time when we're trying to figure out what the time or space complexity is, we have to first figure out what n is, define what n is as a function of like the size of the input, right? And then figure out what the function is doing well enough to be able to count the number of steps necessary and figure out the big O, right? Whether it's the number of steps or the amount of space being used, in this case, the amount of space being used, space complexity is defined as the maximum space used at any point in time while a function is running. So if I give you an algorithm and it's running on some arbitrary input, and that input is of size n, the amount of space it uses is how much new space we use at any point in time during the execution of the algorithm. We'll use big O notation here, and there will be probably some sort of tricks and traps that you'll fall for. So just keep that in mind, right? I'm not here to trick you to like make you feel dumb. The whole point of tricking you in lectures so that you don't get tricked on a quiz or on an exam or like in real life when you're a software engineer, right? So that's something that you need to keep in mind, something to be really aware of and try to be diligent about. The way we keep track of space, first I have to actually describe how space, like what about space we care about. If you think about a computer, right, hopefully this is something you've learned about in your architecture class, but what is the scratch space for a computer? Like what is it called, the piece of hardware in your computer that remembers stuff while you're in the middle of a computation, while your program's running? Where does the program live? What are the different variables? Where do they live? Type it in chat if you know. Yeah, memory, RAM, cache. RAM is what I'm thinking about, random access memory. So there's a part of your computer that literally just, you can treat it as a giant array. And that's where all of your stuff is stored when your programs are running, right? So for example, if you're in the middle of computing Fibonacci or factorial, you will be storing some numbers, some intermediary results in RAM while you're computing and about to return your result, right? So in this case, when we're talking about space complexity, we're just talking about how much space you use in that RAM, right? So you have some sort of array, which represents all of the space that you have while you're in the middle of computation, right? There can be a lot of different slots here. Each slot is the same size, right? This is how I want you to think about RAM and memory in your computer, right? So just imagine there's a lot of slots. I'm not going to try to write them all out. But when you are declaring a variable, for example, that takes constant space. In other words, it takes like one slot, right? So if I say int square braces ARR semicolon, that's just saying a variable now exists that will eventually hold an array. But because we haven't actually declared, like initialized or instantiated the array, just declaring it will take constant space. a single new variable, like if I just said x is equal to 4, that would be constant space as well, right? So we're gonna, for example, if we have a 4 in here, and that's what x is, that's like conceptually what's happening when we say x is equal to 4. In the array, we have some slot in the array. We say that slot is now where x lives, and we put a 4 inside, right? And that's using one unit of space, one slot, so that's constant space. When we start making new data structures, though, that's when we have to keep track of usage. So for example, if we say result is equal to new int array, which is the length of which is defined by some other array. If we have, for example, the old array costing us 10 slots, then maybe our new array will be 10 slots as well. So we would have results here. And it's going to be 10 slots, assuming that the old array was also 10 slots, right? So we have to make a brand new array here, and it takes up 10 slots. And another example is if instead of saying result is a single dimensional array, so 1D array, it's a 2D array. If we still have 10 as the length of the old array, and we're using that to declare our new array and actually make a new array, how much space are we going to use in this case if we think that the old array length is 10? Type it in chat if you know. Yeah, we're getting a bunch of hundreds in chat, and that's true. Someone's asking about recursion and how much space recursion takes. That's a really great question. I haven't answered right now. We're going to answer it next lecture. All right. It is true that recursive functions inherently need to use the call stack, and therefore it needs to use space as well, just to execute on the recursive calls. But there are some times where recursion is as efficient, if not better, than the iterative counterparts. It really depends. Right. Yes, there is a call stack. So when you call functions and another function gets called inside of your function, whether it's the same function or a different function, you create a set of spaces to keep track of all of these functions that you're calling. It's called the call stack. So you can just imagine the same way you would have a stack data structure, that each element on the stack is a different function call that you're keeping track of. So recursion will use up space for that, but it turns out, generally speaking, it's like going to be okay. And it allows you to solve some pretty tricky questions while we're at it. So it's oftentimes more valuable to use recursion, even though it might be a little bit more space intensive. Anyways. So yeah, we would have 100 for result instead of 10 if we were to create a 2D array, because there's 10 slots, and each of those slots is its own elements, its own size 10 array. Are we going to calculate the runtime for recursion? Yes, the answer is yes. So let's go ahead and keep going. So some data structures will actually grow and shrink in size as the algorithm executes. So you can imagine if we had like a linked list, for example, and we add to it or we remove from it, that's going to either make the array elements get bigger or get smaller, right? And that's pretty important. All right, so let's go ahead and take a look at twosum. For those of you who haven't finished homework 0, you're in luck. Part of homework 0 is to ask you to code twosum, and I've included the code here. If the disadvantage to starting late, by the way, for those of you who started on time for the class, is that you have to make up like 2 quizzes, 2 homeworks, and a bunch of other things all in like a week and a half. So we're not really giving them that much of an advantage. Anyways, twosum slow. We're going to try to take a look at this algorithm. If you remember what twosum does, twosum takes in an array of numbers and a target number that we're trying to make. So in this case, let's say we're trying to make 7, and outputs the indices in which the elements will actually sum to 7. So in this case, we're going to get out 1 comma, 1 comma 0, 1, 2, 3, 4, I think, because we would take the 2 at index 1 and then the 5 at index 4, add them together and get the 7, right? So that's what this code does. That's what we want twosum to do. And we're going to look at the best case, the worst case, and the average case runtime, as well as the space complexity here. I'm just going to give you these questions and give you some time to try to answer them. I'm launching a new, oops, wrong poll. I'm launching a new poll now. And I'll give you about 3 minutes to try to answer these questions. We'll do this the same way as before, right? We're going to try to imagine the best types of inputs to take the least number of steps for two-sum that isn't reliant on the size of the input. We're going to try to think about the worst kind of inputs that's going to take the most amount of time for two-sum that doesn't depend on the size of the input. And we're going to do the same thing for average case, like what's typically going to come in. And lastly, we're going to think about how much space it uses. If you have any other questions, feel free to ask right now. Otherwise, I expect everyone to be trying to think and figure this out. So again, what you should be doing is to try to understand this code step by step, trying to understand the Java, and to imagine what is the best case scenario, what is the worst case scenario, and what's the average case scenario. Right? It might take you a little bit to understand the code, especially if you don't feel super comfortable in Java or programming, and that's okay. But try your best, right? We looked at pairs, print pairs in the previous lecture, and that was explicitly to help you kind of understand what happens when we write something like this. So this shouldn't seem too unfamiliar. If you remember print pairs, then this should come back to you as well. Like this should be something you can understand. Okay, you've got about another minute left. So for the 20 of you who are still thinking, you have time, but start trying to come to a conclusion soon. All right, you got about 20 seconds. Go ahead and punch in whatever you're thinking. I'm going to close the poll soon. There's about 6 of you who haven't answered yet. Now 4. Give it your best guess, even if you're not 100% sure. Again, the goal of this is not to be 100% correct all the time. If you were 100% correct and were able to answer every single question in this class that I ask, then you should be teaching this class, right? You should take your A+ and then go do something else with your life. But the whole point of these questions is so that we can make sure that everyone gets a chance to think about it for themselves, try it out, and then we'll go over the answers. So here are the answers that you have. So in this case, a lot of you thought that the best case runtime was O of 1. The worst case runtime was going to be O of n squared. And the average case is probably going to be O of n squared. But some of you thought it was O of n as well. How much space is being used? It's a dead heat. 18 and 18 voting for O of 1 versus O of n, which is really interesting. Let's just go over it now. So the best case runtime in this case is actually O of 1. So best case is actually a similar scenario to what we saw for find index, right? So in this case, two-sum slow will take in some array. Let's imagine it's 1, 2, and then a bunch of zeros, right? Just like a lot of zeros afterwards. It doesn't really matter how many zeros we have, but the idea is that we can arbitrarily make it larger and larger as we want. And then we're trying to find the target, which is 3. So if this is the case, then we're going to iterate through and we're going to try to look at this code. I is currently going to start at 0 if we just started actually executing this argument, executing the code on this argument. I is going to equal to 0 and j is going to equal to 1, right? That's going to be what happens at the beginning. That means array of I is going to be equal. Can I type? Equal to 1. And then array of j is going to be equal to 2. And then we're going to check to see if 1 plus 2 is equal to 3, which it is, so we return right away, right? So we return 0, 1. And you can do this for any arbitrarily long array, which is why we would consider this the best case. So in this case, we would say that the best case runtime is O of 1, right? Because we have this example here, and we can prove that it doesn't matter how big or small the array is, we can always come up with a scenario where this is going to exit out of the for loop right away. Okay, for the worst case, so the best case is all about modifying the content of the input rather than the size. Yes, that's exactly right. And that'll be true for all the other cases as well. I'll give you about 10 seconds. Go ahead and type what you think the justification for the worst case is. Right, so don't hit enter yet, but go ahead and type in what you think the worst case would look like. And it's very similar to the arguments we saw in the previous slides around find index. So that's something to think about as well. And to be clear, the reason why it was O of 1 is because we could exit out of the for loops right away if we had the first two elements equal the target, right? We don't have to go and iterate through a bunch of different times. The size of the argument does not matter and does not change when we have that set up for the array. Okay, hit enter now if you have the worst case justification. So if the target is not in the array, that's what I'm hearing. So we can come up with a case, for example, to some slow, where we take in a bunch of ones, and then we're looking for, let's say, the number 99. Well, we're never going to find 99 by adding two ones together inside of this array, right? So we're going to look through the entire array, which is, in other words, we're going to look through the first, we're going to iterate through the first for loop, and then we're going to iterate through the second for loop, and we're going to check, this one against this one, 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 this one. It's going to go in square times roughly. If you don't know the argument, you can check it out in the runtime lecture from last lecture. We talked about print pairs and we talked about it in more detail. I'm not going to go over it here. But because of that, we know that we're going to not find the 99 inside of the array, which means we're going to go through all of the for loop, the inner and the outer for loops, which means we're going to have roughly n squared iterations. And since the work being done at each iteration is constant, that means we would have O of n squared work, or the runtime in the worst case would be O of n squared, right? So I'll write that here. Now, the average case, again, is where you find the element in the middle somewhere, right? So the average case, I'll do this in blue to be thematic, but the average case is we find our first element about halfway through the array. And if that's the case, that means that we've already iterated through the outer for loop n over 2 times, right? So n over 2 times. And what that means for here is that we had n plus n minus 1 plus n minus 2 plus n minus 3 plus dot 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 plus n minus over 2 plus 1 plus n over 2, something like this, right? So then if we count all of these up, that's roughly like n squared over 2 elements that we're looking at. Is that right? Yeah, it's like 1/2 times n squared, something like that. The math here is a little bit tricky. Yeah, but you can see that there's going to be essentially, I'm not going to try to figure out the exact math. I tried to do this last lecture too, and I realized that I couldn't do it on the fly. But a lot of people are saying that this is n over 2 squared. I'm not 100% sure if that's right. And I would have to write it down on paper, but we don't have the time. But what you need to do is know that this is roughly n squared, even though we've only gone through halfway through the outer for loop, right? Because every time we go through the inner for loop, we're going to go and have, the first time we're going to have n minus 1 iterations, right, of the inner for loop. The second time is going to be n minus 2 iterations. The third one's going to be n minus 3. And then all the way down until eventually, once we're halfway through the outer for loop, I is like halfway between 0 and array.length. Then the corresponding j is going to only iterate n over 2, roughly speaking, times, which means if we add this all together and you do the math out, which we don't have time to do right now, it would still be n squared, which is n(O) of n squared, right? If you're interested in the math, you can, I do not want to explain the math again. We'll have to do that later on. You can watch the video here, which helps a lot. I will also post more information about two-sum by the end of this week, which will be like additional reading that you can read, right? The math essentially is that when we're adding up the inner for loops, how many times each of the inner for loops run, we get this pattern. We have n minus 1 times the first time we have j, this first time we run the inner for loop, we have n minus 1 runs, right? N minus 1 iterations. The second time we go through for the inner for loop, it's n minus 2. The third time, it's n minus 3. And we'll keep going until we eventually get to n over 2 iterations in the inner for loop. And if we add them all up, then that's the total runtime of all of the both the inner and the outer for loops at the same time. And if you do the math out, do a little bit of algebra, you'll end up with n squared. Okay, yeah, so the math for this, I'm not going to try to explain in further detail. If you're interested, there's lecture 3, which you should watch for a very similar case to this. And then I'll explain this in more detail in a document that I will publish later this weekend. Right, so the average case is still n squared. How much space does it use? Now, this is the interesting part because half of you thought it was O of 1 and half of you thought it was O of n. The space usage in this case is O of 1. And here's how we figured that out. So the answer here is O of 1 because, oops, 1 second. Okay. The space is O of 1. Can I bring back everything I just wrote? Nope, it's all gone. O of 1 space because we have all of these variables that I will highlight that get used. So this is one space, this is one space, and this is like 2 slots, right? If you make an array of size 2, it's always going to take up 2 slots in your RAM. Oops. And these will all take 1 slot, right? We will only at any point in time always have 1 I and 1 J. And when we think about how we're going to return at the end of the day, it's going to return an array of size 2, all right? Because it's literally saying make me an array of 2 elements, right? So if we add up all the space, that's 1, 2 plus 2 gives me 4, right? It's always 4. It's not 6 because either this will fire or this will fire, but not both. Creating an array without a variable length is constant space. Yes, right? If you literally know exactly how many elements there are and it's not going to change depending on the size of the input to the algorithm, then it's going to be constant space. So if I make an array of exactly 100 elements, then that's constant space. All right, moving on. So let's go ahead and talk about another version of two-sum. In this case, this is a little bit more complicated. It uses this idea of a hash set. And a hash set, if you don't know it, the first thing you should do is you should type hash set Java. You can see I was doing this in the other section. And then, go down and either look at the documentation from Oracle or maybe look at the Geeks for Geeks example. Whatever helps you learn this is what you should use. But the idea of a hash set, if I had to summarize it, is a container for unique elements. So you can think of this as like a bag that holds some sort of data type, whether it's like numbers or strings or whatever. And you can add to it, which will take O of 1 time. And then you can remove from it, which would take O of 1 time. And you can also ask if something is in it, which will also be O of 1 time, right? Asking contains, removing an element, or adding an element. So this is something hopefully that everyone's seen before in their previous data structures and algorithms class. If not, you're going to have to do a little bit of, studying and research on your own. And we're just going to see how this is used in this code, right? So if we said to sum fast, and let's just pass in like 1, 2, 3, 4, 5. And we were trying to make, let's say, 7. All right. We're going to iterate through and we're going to output some value here. What do you think we should output here in sum fast? I'll give you 10 seconds. Try to think about what should the output be in this case, and then we'll go through it. All right, what do you have? What should the output be? Oh, we got a bunch of different answers. Okay, so some people are thinking 1 comma 4, and some people are thinking 2 comma 3. The output in this case, see, there's two different answers, right? We could say 4 plus 3 plus 4 gives us 7, but also 2 plus 5 gives us 7. This is another case where this will actually output different results than the previous algorithm. And in this case, we're going to output 2 comma 3. That's actually what's going to go on. And let me talk about why that's true. So assume we have two sum fast. We're iterating through. The first thing we do is we define our scene variable, which is just an empty bag right now, right? Again, just think of it as a container which you can put stuff into and then check later on, I mean, constant time, whether you've seen something, right? So in this case, we're going to say, okay, is the element that we're currently at, which is 1, right? J is going to be equal to 0 at the beginning, which means that array of j is equal to 1, which means that we're going to have this other add-in according to the code. We're just following this code, right? So we made our scene variable. We're iterating through the for loop. The first element is 0. And we're going to check to see if the target minus array of j is in our bag. So if 7 is the element that is our target, we subtract by 1, then other add-in should be what? Type in chat if you know. Hopefully this isn't too scary. Type in what you think it is so that I know you're following. We're getting a bunch of 6s in chat. Okay, great. Right? Because yeah, all we're doing is we're subtracting 7 by 1 because that's what the current array element is and that's what the target is. So the other element we're trying to look for, is it in our current bag? If it is, then we're going to return right away, or rather we're going to do this for loop and then we're going to return. But if it's not, which in this case it's not, right, because there's nothing in our bag, we're going to add 1. So now 1's in our bag. We're going to keep going. We're going to say that j is equal to 1, and then that means that our array of j is going to be 2. We're going to ask, is 5 in our bag? And the answer here is no, right? So we're going to add 2 according to our code, because if it's not in our bag, then add the current element at the current index, which is 2. We add 2, we keep going, j is incremented, and then now array of j is equal to 3. That makes other add-in 4. Is 4 in our bag? No, so we add 3 in here, right? From there, we go and look at j is equal to 3, and then 4 here is ARR of j. Now we check to see other add-in, and it's going to be set to 3. Now is 3 in our bag? Yes or no, chat? Hopefully I see like 60 yeses. Yeah, we have this scene hash set, which we've been updating up until now, adding all the elements that we've seen so far. And once we got to 4, we realized that we could make 4 equal to 7 if we only added 3. And since we've already seen 3 in the past, then we are set. We're off to the races. We get to do this inner for loop, right? Because this says if the other add-in, which in this case is 3, because we got 7 minus 4 equals 3. If it's in our bag, that means we've seen a 3 before, which means we can add it to the 4 and get the 7. Then we're going to iterate through from 0 to the array length and try to find some I that's equal to the 3. All right. So we're going to iterate through. At the beginning, we're going to say I is equal to 0. And then is array of I equal to 3? No, it's not. So we're going to move on. I is now equal to 1. That means array of I is equal to 2. Is it equal to 3, this element? No, so we keep going. And then finally, we're going to set I is equal to 2. When I is equal to 2, array of I is equal to 3. So that is equal to the other add-in. I'm just talking about this check here, right? That's what I'm doing when I'm saying is I equal to array of I equal to other add-in. And since it is, we can go ahead and output here. we'll go ahead and return at this point 2, 3, which is exactly the answer we have originally. Do we have to use a hash set for this? Can we not use an array list? If we use an array list, it'll be slower. We could use an array list, but it would take longer to add and check contains, which are the two variables, two methods rather, that we're using here. Now, if you understand all of this, or if you feel like you're kind of understanding what's going on, let's go ahead and try to find the runtime. I'm going to give you some time, set up the poll again, and see if you can find the runtime of this function, which is different from the function from before. So take the time to kind of look through this and see if you can understand what's going on. If you have any questions about what I explained, if you are confused at any point, feel free to ask questions now. But we'll give you about 3 minutes to try to answer the runtime question for all of this. How would the value of j be the second element? You mean here in this return? Is that your question? Well, j is defined in this outer for loop, and since j is in this outer for loop and we're inside of the for loop, we still have reference to j, right? So j is still 3 by the time we find I, so we can return 2, 3. We're literally just saying return a new array of size 2 whose first element is whatever I is at the time, and the second element is whatever j is at the time. At least that's how I understand your question. Let me know if I'm not answering it effectively. So what is the function of the hash set here? Well, the hash set just lets us know whether or not we've seen an element in the past that we might want to care about. So for example, when we're iterating through, we're basically putting things into the hash set so that later on we can check to see if we've seen them in the past. Because if we know that we're trying to make 7, for example, and we're on 4 right now, then if we've seen a 3 at any point in the past, then we know we have the 2 numbers necessary in order to create a sum out of the array that sums to 7. You could use a hash map, and that would work too. The reason why I wanted to write it this way is so that I could trick a few people on the runtime. And some people are already being tricked, which is great, right? So it's used to keep track of all the elements seen. Yep, that's why it's called seen. But you know, if you've never seen this mechanic before, if you've never really worked with hash sets in the past, it might be a little bit confusing. So you know, your questions that you're asking right now are really good. About 20 seconds left. There's still about 14 of you who haven't answered. Go ahead and give it your best guess at this point. What do you think the runtime should be? And if you don't know, what do you think your best guess is? And try to, you know, justify it to yourself as best as you can. But again, the goal here is not to be 100% correct all of the time, right? I'll be closing the poll now, so please vote if you haven't already. There's like 6 of you who still haven't voted. All right. So pretty much the majority of you thought that O of 1 is the best case runtime, and that O of n just barely beats out O of n squared as the best case runtime. It was 46% of you versus 40% of you thought that O of n is the worst case. The average case runtime is O of n, and how much space is being used, people mostly thought it was O of n, right? So let's go over the answers. In this case, we do know that the best case runtime is O of 1. The worst case runtime is O of n, and that's the same for the average case. And the space being used is O of n. And I'll go ahead and take the rest of the time we have to explain why that is. Right? For O of 1, the best case runtime is very similar to the arguments we've been making for 2SUMFAST, right? Best case, we find the elements right away. right? So if we have an input that's like 1, 2, 3, 4, 5, 6, all the way up to however big you want to make the array, but you're looking for a sum of 3, then you're gonna look through the first two elements, and that's a constant amount of work, right? It doesn't matter if you have a for loop to go and look for the elements and look for the index, looking for an I. If you only have the first two elements to traverse through by the time you find it. In fact, you'll find the I almost right away because I is equal to 0, and that's the one we're looking for. All right, so the worst case though, the worst case is interesting. If you have any questions, feel free to ask, but I'm going to keep going because we're short on time. But the worst case here is interesting because we have one of two cases. Worst case, either find the sum or we don't. If we don't, the inner for loop doesn't fire. If we do, the inner for loop fires at most once. All right. So I showed you exactly how the code works just by walking through an example. If you're still confused, that's totally reasonable. Just ask me after section and I'll try to explain it a little bit more. But if we don't find the elements, if we don't find the sum in the array, then the inner for loop will never fire, and the outer for loop takes O of n time, right? Adding elements to an array is O of 1 time. Computing this other add-in is constant time as well. And this if checking contains is also constant time. So this line is constant time, this line is constant time, and this line is constant time. And if the for loop runs in O of n, or if there's n iterations because we didn't find the two numbers that sum up to it, then it's n iterations multiplied by constant time is still O of n. Now, if we do find the elements inside of the array, some of you might go ahead and look at this and be like, hey, I think that the for loop inside of this for loop will cause this to be n squared. In fact, a lot of you voted n squared. 20 of you voted n squared. But if we look at this closely, the inner for loop runs exactly once. And as soon as it runs, we return right away. So it never runs a second time. So we cannot say that it's n squared because if we only run the inner for loop once, even in the worst case when we find the elements, we are looking at the last two elements. We iterate through all of the array in the outer for loop, and the inner for loop only runs exactly once. So that's only an additive factor of n. Right, so that's n from the outer for loop plus the n in the inner for loop, which is 2n. There's not a good way to format this. There we go. Which is n plus n, which is 2n, which is n O of n. All right. And if we look at the average case, it's somewhere in between O of 1 and O of n, but it's probably closer to O of n for the argument that we made before, right? If we found it somewhere halfway, that means the outer for loop iterated n over 2 times, and then it's going to take O of n over 2, roughly speaking, for the inner for loop as well. And again, it's still additive. Why is it n plus n? Isn't it nested? That's a great question. So the reason why this isn't n squared is because normally for an n squared algorithm, let's say we were here and we were looking at print pairs, we run this n times for every time we run this, right? We run this n times, roughly speaking, every time we run one iteration of the outer for loop. Since there's n iterations of the outer for loop, the inner for loop costing us n each time gives us a factor of multiple, like times n. In this case, the inner for loop only runs once throughout the entire life cycle of the function. This only runs one time. So if it only runs one time, it doesn't matter how many times the outer for loop runs because it doesn't get multiplied together. It only gets added together. All right, that's a great question. And I hope I explained it in a way that makes sense. But if you're still confused, feel free to ask me after class. Right? Now for space, the space being used here is primarily dictated by the hash set. Right? This hash set here starts out as empty. It holds nothing. But as time goes on, we're going to slowly add to it over time. And everything else is constant space, right? This is constant space. This is constant space. and then this is constant space, and this is constant space. So it's really the fact that we add to the hash set at most n times in the worst case, because we're going through the entire array, and if we don't find it, then we're going to continue adding to the hash set. If this takes O of 1 time to run that add once, and there's n times that we run this, then the overall space that's being used, the overall size of the hash set at the end of the run, at the end of the function, is n, right? The size of the hash set will be equal to the size of the array, which means we have O of n here. All right. So that's all we had for today. Let's go ahead and jump. Oh, someone said it was a really good example. I'm really happy. I explained it the best in this section. I think I'm going to post a video from this section because the other sections I didn't do as good of a job explaining. So hopefully the video will help people who are still a little bit confused. But there's going to be an additional reading, an optional reading for you to read more about two-sum in order to like understand this better, which should help a little bit. So it doesn't matter how many data structures you use, but how much you change it. Yeah, it's how much you add to the data structure and how it grows over time. It really just means that you have to understand what's going on in your function. And I can explain it, but over time, you need to build an intuition on your own. Anyways, we're at the end here. Let's talk about takeaways. Basically, when we're considering the performance of an algorithm, some deep questions we can ask is the best case, the worst case, and the average case runtimes, right? This goes further than just asking what is the overall runtime of a function, which may or may not be the same as the worst case. It really depends. When we consider space usage, especially when we're thinking about like efficiency's sake, we care about space because we can trade space for time efficiency. If we go back and look at the previous slide, just really, really quickly. Here we go. This two-sum here, the runtime here was better, was way better than the runtime from before, right? The best case runtime was O of 1, which is normal, but the worst case was O of n, which is better than the O of n squared from the previous algorithm, right? This algorithm was not O of n, it was O of n squared. And so, but at the same time, the space it used was O of 1, right? So what I'm trying to say here is that the space we used in this algorithm allowed us to have a worst case runtime that was strictly better, right? Which is nice. So we can consider using more space to trade for time and save time because we, wasted space. We haven't talked about this last point. I'll bring it up later on, so don't worry about it right now. But that's all we have for today. If you have further questions, feel free to ask. Otherwise, thank you for your time, everyone, and I will see you all next week. Or during the homework party, which is on Sunday. Homework party is on Sunday.